So until now we've dealt with continuity by looking for places on a function that are not continuous, and we've looked for functions that can be identified as having a hole or a discontinuity at a point, having a jump, and having no continuity at all because they go opposite or across an asymptote, so they don't have to go to opposite points of or opposite directions toward infinity, but they would be on opposite sides of an asymptote. But for calculus, we want to start to frame our mind to not think so much about where is the discontinuity, but more about defining continuity that can be counted on and depended on, because for much of what we're about to do, you need continuity. You need to be able to say on this interval a graph is continuous, therefore I get to do this to it. So I sort of alluded a little bit just a second ago to what we're going to do, and that's talk about intervals of continuity. All right, so basically that just means if I were to look at a graph, pulling one of these examples up, that has a hole in it, I want to be able to define what's happening on an interval of that graph. So most of the graphs that we deal with are continuous or move from or evaluated from infinity to negative infinity on the domain. But we want to start looking at the graph as what's happening on an interval. And you can see if I were to take an interval here, I'd be able to say that this function is indeed continuous on that interval. It's not a continuous function, but it's definitely continuous on that interval. So let's formalize that idea. If I were to look at this graph on this interval, and I'm going to take an open interval, meaning that the endpoints don't count, what would this look like? Well, I would have a graph that looks like this. It may have a hole, but notice that I'm also sort of considering the endpoints as holes because I'm not including the endpoint. And so this could be an interval that is open on both ends and contains a point at which the function f of x is undefined or discontinuous at f of c, or at c. Let's go with that. Or we could look at this second type as a function that is on an interval that's open, undefined at one point, but specifically undefined as having a limit that does not exist. At some value of c. Or, looking at the other, I can look, oh actually I'm going to look at something completely different. On an interval, I could identify a function as having open endpoints and having a hole in the function, but having f of c be defined. In this case, we'd be able to say that the function is discontinuous on the open interval, that it has a limit at c, but the f of c does not equal the limit as x values approach c. So in one case we can say that there's just a flat out hole, the function doesn't exist at c, but there is a limit. In another case we can describe the discontinuity as having a limit, having no limit at c. Right? So the function exists if one of the holes is complete, but the limit does not exist. And then in a third case we can say that there's a limit at c, meaning from the left and right the function points toward a value, but the actual function at c is someplace other than at that place where that hole is. Alright, so you might be thinking, well, why do I care? That's all the stuff we've already said. But here's why this matters, that we understand it. If we want to define continuity on an open interval, so continuity, at or on an open interval for every point, we'd have to be able to say that for every point on that interval, the f of c is defined, meaning it exists, that 2, the limit as x approaches every c, so each individual limit, if you move c over, that the limit continues to be existent. And that the limit as x values approach c of the function of x, that it equals f of c. And you can see that these are the 3 conditions being defined as not being like this in order to say that the curve is continuous. So what that means is on some open interval, some curve like this, you have an open interval here. We're not talking about the endpoints. Those are outside of the scope of this definition. But that for any c I might choose on the x-axis, at any point, the function itself is, first off, it's defined, it exists. See, this one exists, but it's not part of the limit. That the function exists at c, that the limit points directly to that point at c, and that the limit is, well, I just said that, points exactly to that point. So you have a limit from the left, you have a limit from the right, you have a function defined at c, and in fact, the limit is the same value as c. If all 3 conditions can be shown to be true, then we can say that this function is continuous, on an open interval, and then we would identify between some points A and B. Okay, and that turns out to be very useful for us coming up really soon. Now, let's look at some special cases. Suppose instead we're not able to show that that's true. What we really want is to have a function that's continuous from negative infinity to positive infinity. But when we don't have that, we'll settle for a function that's continuous on an interval except at the endpoints. We can't guarantee that the endpoints are continuous. Well, sometimes if we can't do that, we're okay with, or we're satisfied with, a one-sided limit or one-sided continuity. And that would be seen in the case of, for example, let's give this a value. F of x equals, so this is a root function, and it looks like I have x minus 3, let's call this 3 and 4, x minus 3 and plus 4 outside. So in this case, obviously the function is not defined to the left of its endpoint or its initiation point, or the point that in the parent would be at the origin, but we can say that it's a one-sided limit continuous. So it's continuous on the interval, and we would probably open this interval at this stage of the game to say on the open interval from 3, that would be a negative 3, positive 3 there, on negative 3 to, let's choose some other 7. So on this interval, if I can say without a doubt that I know that this function is continuous, then I can work on that. So sometimes a one-sided continuity is sufficient for me to be able to evaluate and work with a graph or a function. All right, so let's look at closing off these intervals. So instead of saying an open interval, what would have to be true for a function to be continuous on the closed interval? So suppose I wanted to close this interval, what would have to be true? Well, all three of these would have to be true. The inside part is still the same. The limit would have to exist for every c. Every c would have to, or every left and right-handed limit would have to point to c, and or f of c, and that the f of c would have to actually equal the limit. But I would have the additional requirements that on this side, I'd have to be able to say that the limit as x approaches, and let's call this endpoint A and this endpoint B. The limit as x values approach A from the left of this function have to equal the f of A. So the limit would have to be approaching f of A, and f of A would actually have to be included. And so on the other side, same thing. The limit as x values approach B from the right, oh wait, do I have that backward? From the right and from the left, good, of f of x has to equal the f of B. And so now I can evaluate an interval of a function. I may not be able to evaluate the entire function, right? In these cases, the entire function can't be called continuous, but sometimes it's sufficient just to be able to evaluate either the one-handed, the one-sided part of it, or to be able just to eliminate the part altogether that isn't defined and just look at it on an interval. So I'm feeling like it might be time for an example. So we want to use everything that we just did, so let me scroll up a little bit, all of these rules to determine that the square root of the quantity 1 minus x squared is continuous on the interval -1 to 1. So we want to know that it's completely continuous, and in fact we're going to end up showing that it's continuous on the closed interval. So this is called an open interval because the endpoints aren't included, and we want to then go on further to show that it's continuous on the closed interval. So first, let's figure out what the graph looks like. Of course, we could just plop it into a graphing calculator, but it might be a little bit more fun to look at it another way. So I'm going to change f of x to, or look at it directly. So I'm going to change f of x to y, square root of 1 minus x squared. Well, if I square both sides, then I get y squared equals 1 minus x squared. Now this is starting to look familiar. Add x squared to both sides and I get y squared plus x squared equals 1. Well, this is just a circle, right? This is just the equation for a circle. But since we're limiting it on the interval from, well, and we're forced to limit it on the interval from -1 to 1, I'm going to keep it open to begin with because we're not really sure. And then I'm going to alter my domain, or I'm going to restrict it so that I'm only getting the semicircle or the half circle, only because if I went all the way around, which of course this defines for all the way around, if I went all the way around, I would end up with a non-function. In fact, written in this form, I've already eliminated the portion below, but since I've done the reverse math, I have to be more explicit that I'm limiting it to only half of the circle. So I've done that. Now, is this continuous on the open interval? Well, let's look at our rules. The f of c is defined. So our question is, for a semicircle, is there any value between -1 and 1 that I'm not allowed to choose? Meaning I choose any value c, am I going to get an output? And in fact I am, because if I look back at the original function, I have any value between -1 and 0 is going to be something smaller than 1. Squaring it is going to make it positive. So 1 subtract something smaller than 1 is going to give me a positive value and certainly an acceptable value. So first, the f of c, the first test, f of c is definitely defined for every point on the open interval. Now the limit as x approaches c, does the limit exist? And in fact, if every c exists and we know we're getting a smooth curve, clearly the limit exists. So the limit as x values approach c of this function exists. Then, does the limit of the function equal the function at c? Does the limit of the function equal the function at c? I sort of said that already when I was talking about this second one. It's pretty clear that for every value on this curve, if this is c, the limit points toward c, right? The f of c. If this is c, if this is the input c, this is f of c, the limit on both the right and the left-hand side point directly to it. So the limit as x values approach c of the function of x, it equals f of c. All right, so now we've shown that it's continuous on the open interval. Now we just have to test the endpoints to see if it's open, if it's continuous on the closed interval. So let's plug in the f of negative 1, square root of 1 minus negative 1 squared. It's a square root of 1 minus 1, which equals the square root of 0, and that's totally allowed. That just equals 0, and in fact, that's exactly what it equals. So I can color that point in because it's defined as I approach from the left-hand side. I guess I should have more specifically done the limit. If I put in, let me erase this, just so I can be exact and precise. If I put in the limit as x values approach negative 1 from the right, then I'm just going to plug in negative 1. It's no longer a limit. I evaluate it until I get to 0. So we're good there. That's true. And then lastly, the limit as x values approach 1 from the left of the square root of 1 minus 1. Oh, can't plug it in until, hang on. There we go. X squared. So that equals the square root of 1 minus 1. Now I've plugged it in, which equals the square root of 0 again, which equals 0. So I can plug this in, color that in. So I can say I have tested and shown that on the closed interval from negative 1 to 1, the half circle, the semicircle, is continuous at every point. Now I can go do calculus on it, which we're not ready to do yet. So let's look at a couple special cases that continuity may or may not be able to be evaluated. So if I were to graph the tangent function, so we all know that it looks like this. Hang on, let me get all my dots in. That for the tangent function, you have continuity on open intervals. Because of asymptotes, the tangent function never actually reaches, let's call this A and C. And so we know that what we have is continuity on the open intervals between, for example, pi over 2 and 3 pi over 2. So this would have, a tangent function would have various continuities on an open interval, because you can't close in, you can never close in those endpoints by finding a limit. The limits go off to infinity. Another example is sometimes you'll have a graph that'll come along, say we're checking it at C, it'll come along fine, but then as you get close to C, it starts to oscillate back and forth and then goes off again. These oscillations are so close to each other that you can't ever define this as having a limit. It's just, you can't do anything with it. And this would be an example of the f of x equals the sine of 1 over x. So this would be, if you get a graph that looks like that, you can't determine continuity because it just squiggles back and forth so fast. There's no way of knowing what's happening inside of there. But another kind of a squiggle is one that looks, say, like this. Well, I'm going to give you the bounding. I'm going to give you the punchline. This is continuous because of the squeezing theorem. So I have this top function, which I would describe as y equals the absolute value of x, and this bottom function, which would be y equals minus absolute x. And if I had something that came along inside of here, and even though it bounds back and forth and seems to oscillate, it's really, by the squeezing theorem, we know that this function always exists, or that this function is defined and continuous everywhere, because we can see it on the outer edges, and on the inner edges we're bounded by the absolute value. And so you would be able to actually determine all 5 cases to show that this is in fact a continuous function.